Legal stuff quickly, and let's start by putting this in historical context. And I think if you want to put it in historical context in computing architecture, you got to go all the way back to the beginning of it. And so this is actually a quote from Arthur Brooks, who worked with a guy you might have heard of if you're into computers, John von Neumann. And what he's saying is, gosh, here we're building this new thing called a computer, and we really wish we had this big, fast memory that we could store everything in. Unfortunately, we don't. And so what we're going to have to do is use the technologies we have available and build a hierarchy of memories. And that story started then, and we're still living with it today as we work through the hierarchy that we have. The hierarchy that we have currently actually looks like this, if you, and I didn't bother to picture the SRAM caches above this. But we have DRAM, that's our main store. Underneath that, and I say underneath because I'm talking performance-wise, we have NAND SSDs. I'm sure many of you can remember when that wasn't a part of the storage hierarchy. And then underneath that, of course, we still have hard drives and tapes. Why does this work for us? Why is a storage hierarchy useful? It's really because of data locality, which we all learned back in college. But I want to introduce you, and I think actually you already know this, to this 90-10 rule. When we look at the locality of access for data being used in the computer, we often find that 90% of the accesses go to 10% of the data. And that's, of course, why the memory hierarchy works. It's why caching works. But that also implies something about the hierarchies that we build. It basically says each layer as you go down ought to be 10x the capacity of the layer above it. But it can actually be also 1/10 the performance. So it could be 10x the latency of the layer above it. And if you look at the hierarchy we have now and you go from DRAM to NAND, you find that it's actually 1,000x difference, both in terms of capacity and in terms of latency. And so I would argue that we have a gap there. And that's exactly the gap where persistent memory fits. Now, that might sound really convenient. So let me tell you how we walk into gaps like that. And again, putting in this in historical context. If you look at the capacity per die of technologies, of memory technologies across time, you get a chart that looks like this. So we have time on the x-axis. On the y-axis, we have capacity per die. And you can see that across all of these memory technologies, we're getting more dense. We're getting more capacity per unit area. But they're on different slopes. The DRAM slope is actually shallower than the NAND slope. The NAND density is increasing faster. And in fact, the DRAM slope has actually slowed a bit in the last decade. And what we've done is we've created a space along these two technology curves between DRAM and NAND, and that's how we got that 1,000x difference in capacity that I showed you on the last slide between these two. And you can see 3D cross-point memory and that red X coming in the middle in the right place to fill that spot. It's not just about capacity, though. It's also about performance. And from a performance context, we go back to a chart from David Patterson. This is actually a great paper, a very short one. It's a good read, in 2004. And what he said was, gee, I want to go back to his beginning of time was the 70s, not the 50s. And he collected data on various computing technologies and said, how have they increased in performance over time, latency versus bandwidth? And so if the latency had decreased at the same rate as the bandwidth had increased over time, we'd be on that unit axis, on that unit line across the diagonal. Of course, we're not. What happened was we increased bandwidth faster than latency, and so we're north of the diagonal. A really interesting thing, though, when you graph this from a system-level standpoint, I added the NAND SSD points. And what you find is that, remember when you got that first SSD and how great it made your laptop feel? It's because it was moving you back to that same balance point where we started and getting you back to the point where latency and bandwidth was in balance. And that's what we did with NAND SSDs originally. And then, of course, we increased the bandwidth as we tend to do and moved ourselves up. So that's another way in which we're creating space between the top two levels of the hierarchy. And so now I'll name them. Underneath DRAM, we actually have a capacity gap. We wish DRAM was bigger than it is. North of our 3D cross-point, north of our NAND SSDs, we actually have a performance gap. We wish our storage was faster. We wish it took less time to access than it does. And then there is a cost-performance gap that I'll only talk about extremely briefly on the bottom. If we want to improve this memory and storage hierarchy, and we do, of course, we actually have to find some technology that has the right capacity. It has to fit in the system with the right performance. And then, of course, it just has to fit in the system. We have to be able to put it in the system and make it accessible. And I'll go through those 3 characteristics as we go through this, and I describe various solutions to you. So let's start with the memory you may have heard of called 3D XPoint Memory, upon which we'll be basing the persistent memory discussion. And I don't know how much you've heard about it. I'll give you a brief 1-minute tutorial here. There's actually 2 pictures of it on this slide of persistent memory. The one on the left-hand side is a cartoon drawing, and the one in the middle is actually a die cutaway picture. But they're picturing the same thing. In the middle, if you look at that picture, the dark line across the top is actually the bit line going on the left-hand side. And then you see dots above and below that. That's actually the word lines coming towards you. We cut it directly on the bit line axis. And you can see some little dots in between those two. That's actually the elements of the memory cells themselves. So the way this works is you have crosshatched on different planes metal lines. And in between those 2 metal lines, you have an individual memory cell. You can already tell that it's a dense memory because what's determining the XY density is actually just your ability to put those metal lines down, and they can be quite dense. In between each of those crosses is a cell, and that cell is made up of 2 materials, a selector material and a memory material. The job of the selector material is to turn that cell and only that cell on when you bias the bit line and the word line properly. And then the job of the memory element is actually to store the 1 or the 0 or allow it to be read back in the bulk properties of that memory material. The memory material can be written quickly. Since you have metal lines, you're able to have low capacitance and to be able to move that capacitance quickly so you can read and write quickly. And it is also non-volatile, so that memory material is non-volatile. So we get the ability to access at very small sizes, we're quick, and we're non-volatile. Those are the 3 things that we need out of this memory. I guess I didn't say, but it's 128 gigabits also. So we got to put that into the system. We have to fit it into the system. And as I describe this, I'm not just describing what we'll do for an SSD, I'm also describing what has to happen to fit this into the system as persistent memory. The first thing you want to do is have the capacity of multiple die and the performance of multiple die. So we put a number of die down in parallel. One of the things I didn't say about this memory is that in this instance, we're able to do write in place. And write in place is great, unlike NAND, where you have to do an erase and then a write, because it means we don't have to do any garbage collection in these solutions. We have a low latency memory, as I described. We build in all of our solutions a controller, a custom controller, and that controller sits above the memory. It allows you for a single access to go across multiple memory die, so you get the performance of multiple memory die. It's also responsible for doing error correction and making sure that north of that controller, all the data is correct. And it also does carried feeding for the media itself. So there's some media management work that it does. An important aspect of this, for example, is distributing writes, load balancing. And then you have to connect it to the system. And so you need an optimized interconnect to the system for an SSD. This is PCIe NVMe. And on top of that, you have software and libraries to allow you to access it. So the point of this is that you really have to innovate across the system. It's a platform problem to put this new memory, or a platform opportunity to put this new memory into the system. Let's talk about performance. And I'm going to start with SSD performance, and then we'll move on towards persistent memory. As we put Optane into the system, and we're shipping Optane SSDs now, we have decided to use the existing SSD form factors. And so we are shipping SSDs as add-in cards. We're shipping them as 2.5-inch drives because that helps you put them into the system. That is the system fit. That's the lowest friction. It's the easiest way to get them in there. So that's the system fit piece. And we'll talk more about that as we go forward. From a performance standpoint, you get the chart in the middle. And I'm not graphing this the way we usually map storage performance. Even though it is a 7030 IOPS that I'm showing you, I'm actually graphing it the way people graph memory performance. I'm graphing latency at load. And so what I'm showing is along the x-axis IOPS and along the y-axis the latency that you see at that various IOP level. And I'm showing a family of curves. The bottom one is average. And then as you walk up, you're getting to different percentiles. So the next line up is the 99th percentile latency, all the way up to the 99.999th percentile latency. So that means what's your slowest access out of 100,000 accesses. Turns out this is a great way actually to understand the performance of an SSD when you want to put an application on top of it, because you probably know the load you're going to drive, and this allows you to look at that load and say, okay, what kind of a latency distribution am I going to see? And that latency distribution, most apps do more than one storage access, is really important to the performance of the app. And I have Optane on here too, so you can see you can compare the two, right? Except you can't, because the Optane lines are on the axis, and that's no fun. So I'll fix it for you. I'll go to a semi-log plot. And in the semi-log plot, now you can actually see the comparison. That's the same NAND SSD lines that I showed you before. On the bottom, we have the Optane SSD lines, and you can see there is a family of curves all the way from average up to the 5 nines quality of service. And you can see the difference between the two. So even in putting Optane into the system as an SSD, we're able to still get a very large performance difference because we have much faster media, because we've tuned the SSD itself for high performance. And if we were talking storage performance, we would say, okay, if I look at low Q depth, if I look at Q depth 1, a single outstanding transaction in memory lingo, I'm actually getting 6x the IOPS, 6x the performance because of that lower latency. And if I start to look at quality of service, you start to, at a particular load, you could draw between like lines, and you find we often measure this as a 60x advantage. But you could find places where it's actually greater than that. So a huge performance advantage when we put Optane in an SSD form factor and put it into the system. And these are all system-level measurements. I want to introduce one more point, because it's going to be important later, and that is idle average latency. So I walked you through the whole rich distribution, but the thing that you usually hear when people talk about latency is on a very lightly loaded system, when I do a read, what is the latency that I see? What is the average latency that I see? That's the idle average latency. And for a long time, there have been charts like the one on the right-hand side. I drew some of the early ones that show what the latency is for a NAND SSD and what there is for an Optane SSD. This particular one actually splits it out between the SSD itself and between the platform, which is dominated by the storage stack, dominated by the OS running cycles. And you can see that that portion, the green portion, is the same for a NAND or an Optane SSD. But the Optane SSD is way lower latency, way lower idle average latency than the NAND SSD because of the faster media. I'm going to come back to this chart later, but I want to make one more point as we head towards persistent memory. And that is, while I was able to go faster by improving my media and improving my SSD performance from a NAND SSD to an Optane SSD, I have a different problem now. I have a balance, actually, between the system time, that green area, and the SSD time, that blue area. And going faster, getting to lower latency, means tuning both of those. And that really is the magic of persistent memory. OK, before I go there, though, look, we put ourselves back on the line. Isn't that cool? The Optane SSD actually moves us back over to that unit line. And we've put our system back into balance. And that works well, actually, with adding it to the memory and storage hierarchy. So I started out by saying one of the things we wanted to fix was we wish our storage was faster. And we've actually done that. We now do have faster storage in Optane SSDs. Let's go work on that capacity gap, though. I think that's mostly what you guys are here to talk about today. And I showed you that working on the capacity gap means not just going after a faster piece of hardware. It also means going after a faster connection point to the system. And a key piece of that is the storage stack. And I didn't have Neil's email, so I used Linux numbers. Sorry, Neil. Even though I'm picturing a Windows stack. And we've made a number of Linux measurements, and we've gotten it down when you really tune it to about 4 microseconds. I think often it's more like 10 microseconds when it's used in the wild. That's a lot of time to put in front of your really fast SSD, or in this case, in front of your really fast memory. So there's been great leadership to move the operating system, thank you again, Neil, both Windows and Linux to a DAX mode, which allows you to access, do a file open, and then access persistent memory without going through that storage stack. That's a key piece of what you need in order to fit this memory into the system in a way that allows you to access it with low latency. Big deal. So I brought one of them. You guys have probably seen them before. This is an Optane Data Center persistent memory DIMM. This one is 128 gigabytes. It is persistent. It is DDR4 pin compatible, and we have versions of it up to 512 gigabytes. And you notice it looks like memory, which is good. It's direct load store access, which is good. Now let me make a point about how we put this into the system. So I walked you through what it takes to put an SSD into the system on purpose. The story is actually really similar, except for the storage stack piece. When you're putting this thing into the system, you still have to go through the same set of things. So we start with the CPU. In this case, there's some instructions that were added to the CPU that you guys have been talking about. An access will go through the caching hierarchy because it's a load store memory access. There is a new memory controller that'll come out here, and that memory controller understands, and I'll walk through the modes, but understands how to go to either DRAM or to persistent memory. And it also has an interface tuned so that it can connect to this variable latency DIMM. Unlike regular DIMMs, we'll have variable latency here. And it connects directly to the Optane controller, which is housed on that DIMM. The Optane controller is that same kind of controller I was talking about. It's responsible for taking the access, in this case, the cache line access across multiple die so that you get the performance of multiple die. It's responsible for the error correction. It's responsible for the media management. It looks a lot like the solution we did for the SSD, but this is a different controller. It's again, a custom controller. On top of this, we have to have BIOS support. We have operating system support, which we've talked about a bit. We have, thank you, SNIA, the NVM programming model. And of course, applications. And I know that Andy will be talking a lot about those pieces of it here, as he has for you guys many times. The point is, you don't just get the memory and put it into the system. It really is platform-level innovation that's required to make it useful, and that's what we've done here. Where does that get us in terms of performance? Let's go back to that idle latency chart that I was showing you. And I've got, thank you, in the middle, you can see my Optane SSD. It's about 10 microseconds. That is a system level measurement. That's from the operating system. And on the right-hand side, you can see I got rid of all that green because I'm using DAX mode. I'm able to fetch, instead of 4K, which is really the native file system size, I'm able to fetch 64 bytes, a cache line. And I'm able to do that in, well, either 100 nanoseconds if I'm hitting DRAM, or if I'm in app direct mode and I'm going from persistent memory, I'm able to do it in 350 nanoseconds. That's the idle average number that I defined carefully for you before. That's fast. And it's that platform tuning that allows us to do that. How will people use this? There's really two modes that it's important to understand here. The first one is called app direct. I think you might call it persistent memory. In app direct mode, this is the persistent programming memory model you guys are familiar with. The region, there's two regions reported to the system here. DRAM will be one of those regions, just like normal. There will be another region, which is persistent memory. That's read through ACPI. So when you allocate a data structure, you could put it in either DRAM or in persistent memory. It'll be exposed through a DAX file system in Windows and Linux. And there's a number of different ways you could use this. You could use it as persistent memory where you care about the persistence and you're managing that persistence in your application or in some middleware into the system to make sure you're managing the cache, flushing, and everything correctly. You could use it as volatile app direct. In this case, you don't care about the persistence. You don't have to do that management piece, but you have this really high capacity memory, much higher capacity than you had before. Or you could use it as a fast file system. So you could use it as fast storage by putting a file system on top of it. Great example of this one is from a blog by Andreas Schuster, and it's really a poster child app for persistent memory. It's a database in memory. And the thing I really like about his blog is he talks about, hey, I know my data structures, and so I know when I allocate those memory for them, I know what I want to put where. I know what I want to put in SSDs, I'm going to keep it there. I know the volatile memory structures I have, I'm going to keep those in DRAM, and I know that 95% of my data actually is in this column store, and I want that to be persistent. That's what I'm going to put in persistent memory. Now I have a really big in-memory database, and when I come up from an off state, I don't have to reload it. So I increase my availability. It's a really, really powerful message here. And notice he did this by saying, I allocated the memory, and I know where to put things. That's one of the things, that's kind of a hallmark, I think, of application direct usage. Memory mode is the second one. Think of memory mode as simply adding another layer of caching into the caching hierarchy. In this case, that layer of cache is DRAM. And that memory controller on the CPU SoC that I described is actually managing DRAM as a cache. And what this means is you get a really big memory image, and you don't have to change your code. You just get a big memory image. Now, you don't have to change your code, but I have to tell you, if I was you, I'd be thinking about how I can take more advantage of this. Because you may well have had algorithms that were written for the small memory footprint that you had, and now you can think about bigger memory footprint. And we all know, as we write code, that we think about the cache hierarchy that's there to get maximum performance. So while you don't have to change your code first, you might decide from there to tune your code to make it work better. A good example of this, I think, is from VMware, Rich Bruner, where they actually took VMware vSphere, ran it on top of memory mode, and were able to host 3 times the VMs that they could host just because they had the much larger capacity that they could host on a strict DRAM system. And what happens here is not all the VMs are active. The active VMs start, the memory controller demand fetches in the data that they need, and they get to run. And people don't have to change the operating systems they're running in those VMs. They don't have to change the code. So it's an easy way to use this large capacity memory. Okay, we filled that not the last slot, the next to the last slot. We now actually have larger memory capacity, and in fact, it's non-volatile in one of the usage modes as well. I want to say one other thing to you before I stop, and that is there's something else exciting that's happening that's not persistent memory, but I think it's relevant to persistent memory, which is why I want to say it. We're actually shipping now QLC 4-bit per die NAND media. And so that means we have a terabit per die. We can stack 8 of those. You get a terabyte per NAND package. That's a lot of storage. And in fact, we've, with the industry, made something called EDSFF, which is a ruler form factor. That's what I'm holding up. And we'll be able this next year to put 32 terabytes of storage in this form factor. You can put 32 of these into a 1U rack, and that means you have a petabyte per that 1U rack, which is pretty cool. So think about that as your disaggregated storage in your data center, and now think about the fact that you have on your compute node persistent memory, and you could put metadata there, you could put other stuff there. How would you start to build this system in an interesting way? I think there's a lot that can be done here. So I wanted you to see that piece, and it also allows me to fill out my last hole in my triangle. And so now the wonderful thing is I started by saying we wanted a capacity increase of 10x, and we were okay with accepting a latency increase of 10x, and we've actually done it. So we've built out the memory hierarchy here. You can see from the top to the bottom. I'm not saying that every application is going to use every level of this memory and storage hierarchy, but it's there when you need it. And as you build out these PM applications, think about it in the context of that full hierarchy. That's what I came here to tell you today. I appreciate your time and attention. I think I have some time for questions. I left you all speechless. I'm okay with that too. Yes. I have a question. Was that persistent fun?
Al Wegener with Anacode. Intel doesn't have a great reputation for delivering, I'm sorry to say this, on 3D XPoint. So is there any reason why we should believe your claim that 32 terabytes in a ruler will be available later this year?
That's not 3D XPoint, that's NAND. So when I said 32 terabytes in a ruler, I'll answer your question you actually asked and the one you actually meant. When I said 32 terabytes in a ruler, I was actually talking QLC NAND. I want to be really clear. We're actually already shipping 16 terabytes in this form factor. And I think that's the best indicator that we'll ship 2 terabytes in this form factor. I think you were really asking me, well, I don't want to put words in your mouth.
Yes, when will 3D XPoint ship in volume?
3D XPoint is already shipping in volume in SSDs. 3D XPoint is the memory. It's shipping in volume in SSDs. I don't get to tell you when we introduce this. What's that?
I don't consider 100 units a quarter volume.
We're actually shipping millions of Optane memory units in client.
Then why don't you publicize that?
I thought we had. No? We are shipping 3D XPoint in volume. I think you're asking me about the memory piece, or you're just asking me about the technology? Either way? Okay.
Nathan Brookwood, Inside 64. I'm known for asking easy questions.
Where are you?
I'm over here.
Ah, thank you.
Okay. But I was curious, when you jam that petabyte into the 1U bot container, how much power is it going to take?
That's a good question. So I think the key with jamming a petabyte into 1U, and I'm talking about QLC SSDs, is that you're talking about your bulk storage. It's the cooler storage, and you're probably not firing up all of those SSDs into full write mode at the same time. You're only writing on some of them. You're only reading on some of them. Some of them are in a lower power state. I'm not here to tell you that you'd want to be writing full bore on all of those SSDs in parallel. But I don't think that's the usage model you're going for here. I think you're going for big bulk store. I want to make sure it was really clear. I was talking at the very end about NAND, not 3D XPoint. You guys got it? This is Optane, and this is NAND SSD. I don't want to confuse.
So in the model where you showed that you could use the persistent memory to expand the memory pool, if the application doesn't understand their different classes of memory, then is that tiering managed by the operating system or by the memory management unit, or does it just treat all the memory as the same class even though it's sort of like different performance levels?
So I think Andy's going to tell you a lot more about this, but I'm not sure which mode you're talking about. In the application direct mode, you would know that it's a different class of memory when you allocated the memory. In the memory mode, you wouldn't know, and it would be managed for you by the hardware in the system. So you have a choice.
We have time for one more question. So.
Just so I got the scale right, my name's Steve Leibson. I'm with EE Journal, by the way.
Yeah.
100 to 350 nanoseconds for Optane used as persistent memory. In that scale, what is your number for DRAM, just so I have a relative number?
In that scale, I think what I said in the slides was it was less than 100 nanoseconds.
Yeah.
Probably, and I'd be guessing if I gave you a better number
Okay,
than
could
that.
you say less than a microsecond for
Less than
Optane? for Optane on that
Yeah,
same
I was
slide.
trying to build out the
Yeah, I
hierarchy.
know.
But you know, it is when I'm comparing it to DRAM, I'm comparing it to the register access for DRAM. So it's not the 30 nanoseconds you usually get at just the component itself. I think it's more like 70 nanoseconds. I haven't measured that one myself, so I'm comfortable saying less than 100. Sure.
Very good. Let's give the speaker a hand again.
Thank
That's
you.
good.